Atomic structure, the particles that make up an atom. Atoms are very small, and the particles that make them up are even smaller, the protons, neutrons, and electrons. We measure the mass of these particles in something called the atomic mass unit, which is abbreviated U. It's kind of a complicated number, but it's based off 1/12 of the carbon-12 atom. Carbon-12 means it's carbon that weighs exactly 12. And so it's given a value of 1.66 times 10 to the negative 24 grams. We won't use that atomic mass unit that much, but it is very helpful when we're thinking about the specific masses of the particles. For example, proton, which we're going to abbreviate P positive, because it's a positive particle, has a mass of almost exactly 1 atomic mass unit. Neutrons, which we call N0 because they're neutrally charged, also weigh about 1. These are the two particles that you're going to find in the nucleus of the atom. See the picture. Electrons move around the nucleus, but they have a mass much smaller than the protons or electrons, at about 1/2000th of the mass of the proton or neutron. So their atomic mass is 0.00055 U. This picture you're seeing is inaccurate in the fact that you can actually see the nucleus in an atom. The nucleus is actually very tiny, in the magnitude of 10 to the minus 5 times smaller than the atom itself. That's the equivalent of having a baseball in the center of a gigantic baseball stadium. Okay, the nucleus is so tiny we actually couldn't imagine seeing it. We just have to imagine it's there. How we write the symbol of atoms, let's look at sodium-23 as an example. The symbol sodium is Na, which is Latin for natrium. 23 stands for its mass number. This is how many atomic mass units it would weigh. It's the sum of the protons and the neutrons. We don't include the electrons in the mass because they're so much smaller, so we just ignore them. The blue number is the atomic number, and that's kind of the identity of the atom. That's just the protons only. So we write sodium as 23 over 11, but sometimes we can skip the 11 because anything with the atomic mass of 11, the atomic number of 11 has to be sodium. So sometimes we'll write it as Na-23. The number of neutrons is easily determined by taking the atomic number and subtracting the mass number. And if you're wondering how many electrons are there, as long as the atom is neutral, the electrons, which are negative, will equal the protons, which are positive. The negative and positive therefore cancel one another out, giving a neutral charge. You might have two atoms that you could call sodium, but they're different weights. These are called isotopes from one another. The one on the left has 11 protons and electrons. The one on the right has 11 protons and electrons. The one on the left has 12 neutrons. The one on the right has 13 neutrons. Chemically, they'll behave exactly the same. But the difference is the one on the right weighs just a little bit more. This happens quite often in nature. Carbon has 3 isotopes, 2 of which are not radioactive, carbon-12 and carbon-13. Each of them has 6 protons, but carbon-12 has 6 neutrons and carbon-13, 7 neutrons. There's also carbon-14, but it's radioactive and so very short-lived. Sometimes atoms aren't neutral. They're ions. If an atom is neutral, the protons and neutrons are equal to one another. But if it's a negative ion, we call it an anion. And in that case, you have more negative electrons than you do protons. Cations are positive because you have more positive protons than you do electrons. Looking at the two pictures, you can see the cation on top has 2 protons and 1 electron. We'd say it had a charge of +1. The anion on the bottom has 3 electrons for its 2 protons. We'd say it's a charge of -1. You try a question. How many of each of the subatomic particles would be in 33 over 16 S-2? Pause the video and give it a try. All right, did you get these answers? I hope so. Next, let's take a look at how we get the mass that we find on the periodic table. Look at these 6 elements. You'll notice that in addition to their names and symbols, we see 2 numbers. The number on top is the atomic number. It's always a whole number because you can only have whole numbers of protons. There is no such thing as a fraction of a proton. The number on bottom is the mass, and it's always a decimal. never will you find an atomic mass, that's an exact whole number. So how do we get these numbers on the bottom? Well, actually, they're the average of all the isotopes that we could naturally find in nature. Look at this example problem. Knowing that the average atomic mass of magnesium is 24.3050 atomic mass units, we get that from the periodic table, which of the following three naturally occurring isotopes is the most abundant in nature? What do you think? Well, the correct answer is magnesium 24. We can tell that because the average is closest to magnesium 24. And so, however they came up with that average, we know there's more magnesium 24 than any of the other isotopes simply because it's closest. This is what we call a population average. Look at this picture on the next page, and let's think about beans. Let's imagine the blue bean weighs 10 grams and the red bean weighs 20 grams. So when we say, well, what's the average of all beans, you might be tempted to say 15 grams. That doesn't work, though, because you have more of the 20-gram beans than you do the 10-gram beans. Actually, the average mass is 17.5 grams. How did I get that? Easy. What we do is we take the mass times the fraction that's represented. So 25%, or 0.25, of the beans are blue. Multiply that by 10 grams. 75% are red. Multiply that by the 20 grams. That gives us 17.5 grams. So let's try calculating an actual atomic mass. Remember, the average atomic mass is not the weight of all the isotopes divided by the total number. That's incorrect. What you have to do is you have to take the sum of the mass times the fraction, usually expressed as a percentage. Let's calculate the atomic mass of neon from the masses of abundances in its three naturally occurring isotopes. Pause the video, give this question a try, and then check your answer. Did you do it right? In this case, we can see that the average atomic mass is 20.1797 atomic mass units. This is the same you'd find on the periodic table. For each of the three isotopes, you would take the mass that's given, for example, 19.99244, multiplied by the decimal equivalent of its abundance, and then you would add that to the same thing for the other two isotopes. Good luck studying subatomic particles in atomic structure.